Hi everyone. Today we're going to finish 18.1 day 3, and that is on angle rotations and radian measures. And because this is the last day of the lesson, we are going to involve the real world problem solving involving arc length. So let's take a look at some review information here. Recall that from the previous notes that for a central angle theta in radian degree measure, the theta is actually equal to S over R, where S is the intercepted arc length. Now, if we want to cross multiply, we're going to have a different equation. So S times 1 is S is equal to R times theta. So that's going to be the new arc length formula. So let's make a note that radius R stands for the radius, and theta is the angle measured in radians. So if the angle is not in radians, then we need to do a conversion to convert from degree to radian. So that's just a side note. Also, as a note, many problems involving arc length also involve angular velocity, which is a concept that is more familiar, more widely used in the topic of physics related problems. So the angular velocity is the angle measured through which an object turns in a given time interval. So that's kind of like what theta is equal to. And then 1 revolution is 2 pi r and 2 pi radians. Let's take a look at the first real-world situation. John is adding a curved edge to the landscaping in front of the high school. The curve is an arc of a circle with a radius of 1,600 feet. The central angle that intercepts the curve measures pi over 8 radians. Find the length of the curve to the nearest foot. So let's draw a representation of the scenario here. So here is the landscape in a curved edge, and the angle is pi over 8 radians, and the radius is 1,600 feet. So this is the kind of what the situation looked like, and they want to know what is the length of the curve. So this is S we're looking for. So given the formula that we just learned, S equals R times theta, we know that the arc length is the radius, which is 1,600 feet, times the central angle in radian, and since it's pi over 8, it's already in radian, and we can just go ahead and cross cancel. That would be 200 pi, and that's feet, and that is approximately 628 feet. So that is how long the arc length is for the curve edge. That's the end of the problem. Let's take a look at another one. San Antonio, Texas is located about 30 degrees north of the equator. If Earth radius is about 3,959 miles, approximately how many miles is San Antonio from the equator? So if we take a look at the situation here, this is kind of like a representation. And here is the equator, here is the 0-degree equator, the biggest circle right here. And let's pretend that here is San Antonio, Texas, which is 30 degrees north of the equator. So here's north. And then, so we have the central angle here. From here to here is actually 30 degrees. So if you want to know how far it is basically for San Antonio, Texas, how far is it away from the equator, we're basically looking for the arc length. So S is what we're looking for. So once again, using the formula that we just learned, S is equal to radius, which is in this case 3,959, times the central angle. And remember, the central angle needs to be in radians. So we have a 30 degree is the angle, and we need to do a conversion to turn it into radian. It's going to be times pi over 180, cross canceling, and we just have pi over 6 is the angle. And we're going to substitute it in here for theta. And then doing the math, we should have 2,073 3 miles, and that is how far San Antonio, Texas is away from the equator. And that's the end of this problem. Next, let's take it into space. Taking a look at the problem here, we got Earth equator is at a latitude of 0. So again, sort of what we drew earlier. Here's the equator at 0 degrees. Okay, and then the Arctic Circle is at a latitude of 66.52. So if you kind of look at the big circle that involves the equator, it kind of looks like this flat. And then the one on top is going to be your, so if you think of like, this is a bigger piece of the globe. So, this equator, this is kind of like a piece. The Arctic Circle is right there. And it is at 66.52 degrees north. And then the diameter of the equator, which is from here to here, is 7,926 miles. The diameter of the Arctic Circle is 3,150 miles. So if you see that the Arctic Circle is actually a smaller circle than the equator, that's why the radius is going to be smaller than the equator's radius. Question part A says, find the angular velocity in degrees per minute of a point on the equator and of a point on the Arctic Circle. So we are to find the angular velocity. And the hint here is that the Earth completes one revolution of 360 degrees in 24 hours. So it doesn't matter if you're on the Arctic Circle or on the equator, you're always going to be traveling 360 degrees in 24 hours. So for this problem, it's just a conversion because we need to find the angular velocity, which states that it is in degrees per minute. So we have a 360 degree. So this is angular velocity we're looking for. 360 degrees in 24 hours, but we don't want hours because we want minutes. So we're going to convert from 1 hour to 60 minutes. And notice that the hours will cancel out. That leaves us degrees per minute. And that is what angular velocity is going to be measured at, degrees per minute. So if you do the math and just divide 6 by 24, that's going to be 1/4, which is 0.25 degrees per minute. And that is the angular velocity for the traveling speed from either on the equator or on the Arctic Circle. That's part A. Part B, how far does a point on the equator travel in 15 minutes? So if you're just jumping on this dot, in 15 minutes, basically, how far can you travel? So you're looking for the arc length right there. So this problem we need to understand by starting with the rate that we just found, and then we need to actually multiply that by the time, because distance equals rate times time. Remember that formula? So we're looking for the distance that it can travel in 15 minutes. So the rate is 0.25 degrees per minute times 15 minutes. And notice that minutes will cancel out. So we have 0.25 times 15, which gives us 3.75 degrees. And that is how far it will travel in 15 minutes. So that is the end of part B. And part C says, how long will it take a point on the Arctic Circle to travel this distance? So we just know that we are going on the equator. If we follow this equator for 15 minutes, so let's assume that from here to here is 15 minutes we traveled, and that is 3.75 degrees. Well, how long it's going to take for it to travel on the Arctic Circle? So basically, how many degrees is it going to be there? And how long will it take? Like how many minutes is instead of 15 minutes travel. How many minutes is it going to travel on the Arctic Circle? So the first part that we need to do here is actually a conversion from the 3.75 degrees compared to a 360, the full circle. So basically we're taking the ratio and set that equal to how many minutes would that be compared to traveling on the, not minutes, how many miles will that be compared to the entire circumference, which is 2 pi r, or pi times the diameter, which is the diameter for the equator is given in this case is 7926 miles. And so if we cross multiply, we will have 360x equals 7926 pi times 3.75. Dividing by 360 on both sides will give us the final answer of about, and you should use your calculator at this point to verify the answer. You should get 259.4, and that is miles traveled in 15 minutes, remember. Okay, because we just traveled 15 minutes. So next, we're going to use that same number, and we're going to convert that back into a degree. So because we started with degree, we're going to end up with a degree to see how many degrees is equivalent in the Arctic Circle, because we are going to now move over to the Arctic Circle. So using the 259.4 miles over, we do not know how big it is the Arctic Circle, but we can calculate it. The circumference is 2 pi r, or pi times the diameter, which in this case is 3150. Well, we set that equal to how many degrees to 360 degrees. Well, how many degrees out of that 360 degree traveled? Cross multiplying again, we have 3150 pi. X is equal to 360 times 259.4 miles. Dividing by 3150 on both sides, pi, we will be able to get x, which is approximately, and you should again do the math on your calculator to make sure it agrees, and it should be 9.437. So we have finished converting that 3.75 degrees is actually equal to 9.437 degrees on the Arctic Circle. So remember, this is the Earth equator, and this is on the Arctic Circle. So they're equivalent, okay? Because of it's different because of the radius of the two different circles. And now we're going to figure out how long it will take to travel that 9.4 degrees. So we're going to go back to distance equals rate times time formula. Well, we already know the distance travel is going to be 9.437 degrees. The rate we're traveling, remember, it is the same speed, okay? It's 0.25 degrees per minute. Well, times the time, because we do not know, we're going to let it be t, time t minutes. We're going to divide both sides by 0.25. And that will give us the time, I'll just put it here, is approximately 37.75 minutes. And that is how long it is going to take for the dot to travel on the Arctic Circle, to travel 9.437 degrees, which is equivalent to traveling 3.75 degrees on the Earth equator. So 37.75 minutes. And that is the end of the problem. That was a long problem. Example 2b, different problem now. A neutron star, which is an incredibly dense collapsed star in the Sagittarius galaxy, has a radius of 10 miles and completes a full revolution every 0.0014 second. A, find the angular velocity of the star. in radians per second. So angular velocity is given by 2 pi radians divided by the radian, which is, remember, angular velocity is just the angle that we're looking for, theta. So it is actually equal to 2 pi radians divided by 0.0014. And that's going to give us 4,490. This is radians. That's radians per second. So that would be the angular velocity, the speed. Next, use this velocity to determine how far a point on the equator of the star travels each second. So to find out how long it travels, it involves the arc length. So S equals R theta. And theta, again, is what we just found right here. So it's equal to, the radius is actually given on top right here, 10 miles. So we're going to multiply 10 times theta, which is what we just found, 4490. And that's going to give us approximately 45,000 miles. And that's how far per second, each second it traveled. Now, how is this speed compared to the speed of light? So we have about 4,500, actually 45,000 divided by the speed of light, which is 186,000. So if you divide it, you actually get a decimal of 0.24, and you can use your calculator to verify. And turning that into a percent is multiplying by 100, which is 24%, which is close enough to 25%, which is about 1/4 the speed of light. So compared to the speed of light, it's about only 1/4 the speed of light. And that is the end of the lesson. So go ahead and get started with your assignment. And again, go ahead and log into Google Classroom to check out what is your assignment for today. And that is it. Have a nice day, everyone. See you next time.